Hello there, and welcome to the Sleepy Thought Channel. Tonight, we're drifting far beyond the familiar world beneath our feet and into one of the greatest mysteries the universe has ever offered us. Out there in the dark, between the stars' planets circle, distant suns, frozen moons hide oceans under ice, and strange signals cross the sky with no easy explanation. Some worlds may have the right hair, the right chemistry, or the right warmth for life to begin. Others may hold clues that something has already stirred somewhere far beyond Earth. This is what makes the search so captivative. We are no longer only imagining life in space. We are learning where to look, what to listen for, and which signs may reveal that the cosmos is not as empty as it once seemed. The answers may be hiding in the atmosphere of a faraway planet beneath, a crust of an icy moon, or inside a signal that refuses to be forgotten. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, to one sleepy soul at a time. But for now, all you need to do is settle in, let your shoulders relax, and notice your eyes grow heavy. And as the day begins to gently fade away, join me as we explore this fascinating search for life together. Let's begin. There may be more habitable worlds than anyone once dared imagine. For most of human history, Earth looked like a miracle that might never have happened twice. Now that feeling has changed. Astronomers have learned that planets are not rare decorations around stars. They are everywhere. Many stars seem to host entire families of worlds, and a surprising number orbited distances where liquid water could exist. That does not mean those places are alive or even pleasant, but it changes the scale of the question. The universe may not offer one lonely stage for life. It may offer millions or billions. Some of those worlds will be scorched, some will be frozen, some may have thick skies, deep oceans, or climates that shift in ways we can barely imagine. What matters is this: the ingredients for possible habitability do not seem extraordinary anymore. That realization is thrilling, because it means life may not need a miracle. It may only need a chance. We have already confirmed more than 6,000 planets beyond our sun. That number still feels almost unreal, because within living memory, the count was zero. For centuries, planets around other stars belonged to philosophy fiction and wishful thinking. Then the first detections arrived, and the trickle became a flood. Now astronomers have found worlds larger than Jupiter, worlds smaller than Earth, worlds that race around their sea, stars in days, and worlds that drift much farther out in darkness. Each new discovery has widened the imagination. These are not just dots on a chart. They are real places with gravity, weather, sunlight, and histories. Some may have raging winds of vaporized metal. Others may be wrapped in clouds, so thick that no surface can be seen. The astonishing part is not only the number, it is how quickly the universe changed, from mostly empty in our minds to crowded beyond belief. We are no longer asking whether planets exist elsewhere. We are sorting through a cosmic multitude. Some nearby worlds sit where alien oceans could stay liquid. That is one of the most captivating ideas in modern astronomy. Not on the far side of the universe, but close by in cosmic terms. There are planets that circle within temperate zones around their stars. In those regions, a world with the right pressure and atmosphere might keep water from freezing solid or boiling away. That possibility turns a distant point of light into something far more intimate. You can picture it: rain falling under another sun, clouds gathering over a dark, sea waves moving across a shore no human has ever seen. Of course, distance from a star is only the beginning. A planet can sit in the right zone and still be barren, airless, or blasted by radiation. Even so, the existence of these candidates matters enormously. It means the idea of an ocean world beyond our solar system is not fantasy anymore. It is something nature may have already built nearby, waiting for us to understand it. Life in space may first be found as chemistry, not creatures. That is a beautiful and humbling thought, because our first encounter may not be with anything that waves, swims, or looks back. It may come as a pattern in molecules, a strange mix of gases that should not coexist unless something keeps renewing. them a chemical signature that looks restless, unbalanced, alive. In the deepest sense, this changes the search completely. Scientists are not only hunting for alien animals or forests, they are looking for atmospheres, minerals, and reactions that hint at metabolism from far away. In a sense, they are trying to detect the breath of a world that makes the whole effort feel both more subtle and more profound. Life does not need to announce itself with cities or radio towers. It may reveal its presence by quietly changing its planet over time. Before we ever see a body, hear a signal, or know a shape, we may first notice that somewhere in the dark chemistry has begun behaving like biology. A distant atmosphere might whisper life long before we see it. When a planet passes in front of its star, a tiny fraction of starlight filters through the air around that world before reaching us. Hidden inside that light are clues. Certain gases absorb certain colors, leaving faint fingerprints that careful instruments can detect from unimaginably far away. Astronomers can begin to ask astonishing questions. Is there water vapor? There. Carbon dioxide making something stranger. An atmosphere is more than air. It is a record of what a world has been through, and perhaps what is happening on it right now. On Earth, life transformed the sky over immense spans of time. That is why alien atmospheres matter so much. They may carry traces of oceans' climate geology, or even ecosystems at work below the clouds. We may never see an alien shoreline directly, but we could still learn that a world has seasons weather and a chemistry that refuses to stay still. That would be enough to change everything. Europa hides a dark ocean beneath ice thicker than mountains. At first glance, it looks like a frozen, lifeless moon. Its surface is pale, cracked, and bitterly cold. But beneath that shell lies one of the most tantalizing places in the solar system. Evidence suggests that deep below the ice, Europa holds a global ocean with more water than all of Earth's seas combined. That alone is astonishing. Then the imagination begins to move down there. Shielded from radiation and locked away from sunlight, an alien sea may be pressing against rock on the ocean floor. If heat rises from the interior, and if chemical reactions are feeding that hidden water, then Europa may have some of the ingredients that made life possible here. It would not be a bright, friendly world. It would be black, crushing, and cold above. Yet under that frozen lid, there may be currents chemistry, and perhaps environments where living things could survive. Few places feel so silent on the outside and so suggestive. Underneath, Enceladus sprays ocean water into space for us to sample. That sounds almost too generous to be true. One of the greatest places to search for life may be sending pieces of itself output, as if Saturn's tiny moon cannot keep its secret completely. Hidden near its south pole, enormous cracks vent plumes of water vapor, ice grains, and other material high above the surface. Those plumes come from a buried ocean below the ice, instead of drilling down through miles of frozen crust. Spacecraft can fly through the spray and taste what the moon is throwing into space. That is extraordinary. It turns a sealed ocean world into something testable. The more scientists studied those plumes, the more compelling Enceladus became. Salts, organic compounds, and signs of active chemistry all make the moon feel less like a dead ice ball and more like a working system. If any place in our solar system seems to be inviting investigation, it is this small, bright world sending its hidden sea into the dark. Mars still teases us with organics, methane, and unfinished questions. That is part of what makes Mars so compelling. It is not clearly alive and not clearly dead in the way people once imagined. Instead, it keeps offering clues that feel important without becoming a final answer. Ancient riverbeds, lake sediments, and minerals show that the planet was once wetter and more Earth-like. Then came discoveries of organic molecules preserved in old rocks, along with puzzling hints of methane that seem to appear and change over time. On Earth, methane can come from living things, but it can also come from geology. That ambiguity is exactly why Mars remains so fascinating. Every clue seems to open two doors at once. One leads toward biology, the other leads toward strange chemistry. In a world that used to be far more hospitable than it is now, Mars is not captivating because it solved the mystery. It is captivating because it keeps refusing to let the mystery die. The search for alien life now includes technology, not just biology, that widens the story in a thrilling way. Scientists are not only asking whether microbes might exist on distant worlds, they are also asking whether intelligence might leave detectable marks on the planet. In space or across the sky, a civilization might produce narrow radio signals that nature rarely makes. It might create artificial light industrial chemicals or excess heat from enormous energy use. In other words, it may be possible to notice not just life, but activity with intention behind it. That idea gives the search a different emotional charge. Biology can fill a world with silent abundance. Technology can alter a world in ways that travel across vast distances. Of course, this is a difficult game because nature is clever and human interference is everywhere. Still, the search matters because it accepts a bold possibility. Somewhere intelligence may already have changed its environment so dramatically that the universe itself has become the message board. One strange radio burst in 1977 still haunts astronomy for just a brief moment. A powerful narrow band signal appeared in data from an Ohio radio telescope strong enough and unusual enough to make an astronomer circle it and write one unforgettable word beside it: wow. Then it vanished. It was never confirmed again, never repeated on command, and never explained in a way that settled everyone's nerves. That is why it lingers. The signal seemed to have qualities that made people dream of a transmission rather than a natural source. Yet science is cautious for good reason. A single event is not enough. The universe is full of noise interference and phenomena that can mislead even careful observers. And still, that fleeting burst continues to hold its place in public imagination because it captured a perfect tension. It was not proof, it was possibility. For 72 seconds, the sky seemed to say something unusual. Then it fell silent again and left humanity listening even harder. TRAPPIST-1 packs 7 rocky worlds around one tiny star that alone makes the system feel almost impossible, like a set of miniature planets. Tucked close around a faint red ember, TRAPPIST-1 is much smaller and cooler than our sun, yet it hosts 7 worlds that are all roughly Earth-sized, all squeezed into an N. Orbital arrangement tighter than anything in our own solar system. If you stood on one of the outer planets and looked up, some of the neighboring worlds would appear enormous in the sky, hanging there not as stars, but as visible planets with phases and motion. The years are incredibly short. Some complete an orbit in only a few days. What makes the system so captivating is not only the number, but the intimacy. This is not one lonely candidate for life. It is a whole architecture of possibility around a single star. Nature did not build one intriguing world there. It built an entire train of them, almost daring us to ask which one matters most. 3 TRAPPIST-1 planets set inside the star's habitable zone. That is why the system seized the imagination so quickly. Out of those 7 packed worlds, 3 orbit at distances where temperatures could allow liquid water on the surface if the planets have the right atmospheres. That phrase matters. If the habitable zone is not a promise, it is an invitation to investigate. Even so, the idea is astonishing. One small star may have not one but several worlds that fall into the most talked about range for possible life. In our own solar system, the concept of a life-friendly world once seemed rare and precious. Here nature appears to have arranged multiple chances in a single place. The star glows redder and dimmer than the sun, so the light on those worlds would feel different, perhaps like permanent sunset. Yet somewhere in that compact system, there may be rain clouds or seas. Not certainty, but a cluster of possibilities circling in the dark. Proxima Centauri b circles the nearest star to our sun. That fact gives it a special hold on the imagination because it means the newest known exoplanet is not hidden in some unreachable depth of the galaxy. It is right next door in cosmic terms, orbiting the closest stellar neighbor to our own system. Even so, next door in space is still astonishingly far away. Light takes more than 4 years to cross that gap. If Earth ever sends a true interstellar mission, this world will always be near the front of the line. The planet itself is thought to be roughly Earth mass, which immediately makes people wonder about rocky ground skies and oceans. Yet its star is a red dwarf, and red dwarfs are not calm companions. They flare, they spit radiation, they complicate every hopeful picture. That tension is what makes the world so compelling. The closest candidate for habitability may also be one of the harshest, as though the universe placed possibility nearby but refused to make it easy. K28b may be a waterage high sea and world. This is where exoplanets begin to feel wonderfully strange. Rather than being a simple Earth twin, this world may belong to a more exotic category altogether. A Hysian planet is thought to have a deep global ocean beneath a hydrogen-rich atmosphere, creating conditions unlike anything on Earth, but perhaps still capable of supporting life. K28b is larger and heavier than our planet, so if it does have an ocean, it would not be a familiar blue world with continents and beaches. It could be a place of immense pressure, thick air, and chemistry shaped by an entirely different balance of gases. Or drew so much attention was the atmosphere observations revealed carbon-bearing molecules that fit intriguingly with this picture. That does not prove an ocean, and it does not prove life, but it suggests that habitable environments may come in, formed stranger than the ones we first imagined. The universe may not favor Earth copies. It may favor surprises. Some planets could hold oceans with no continents at all. Try to picture a world where there is no shoreline anywhere, no rocky coast, no island chain rising above the waves, just water, planet-wide stretching beyond every horizon. Such places may exist, and if they do, they would force us to rethink what a habitable world even looks like on Earth. Land shapes weather, nutrients, and cycles that life depends on. Remove the continents and the whole character of the planet changes. Winds would race over uninterrupted seas. Storms could gather over vast distances. The chemistry of the deep ocean might control everything. Some of these worlds may have water layers so immense that the pressure below forms exotic high-pressure ice, sealing the liquid ocean off from the rocky interior. Others may retain deeper circulation. That difference matters because contact between water and rock can feed important chemistry. So a water world sounds dreamy, at first almost serene, then it becomes stranger. Endless ocean may be beautiful, but it may also be biologically complicated. Some exoplanets may stay warm under thick hydrogen-rich skies. That possibility expands the search for life in a bold way because it suggests warmth can come from more than just perfect Earth-like conditions. Hydrogen is a light gas, and in a thick atmosphere, it can trap heat very effectively under the right circumstances. That means a world farther from its star than we might expect could still maintain temperatures suitable for liquid water. It is a reminder that habitability is not a narrow little target painted only for Earth copies. A planet with unfamiliar air could still be clement at the surface, even if its skylight and weather bear little resemblance to anything we know. Of course, such a world would feel alien in every sense. The pressure might be immense. The atmosphere might be hazy or chemically unusual. Yet from the perspective of life, warmth and stability may matter more than familiarity. A planet does not need blue skies and breathable air for humans. It only needs conditions where biology can persist. A red dwarf's habitable zone sits dangerously close to stellar flares. That is the cruel twist in one of astronomy's most hopeful stories. Red dwarfs are the most common stars in the galaxy, which means the number of planets around them could be enormous. Many of those planets orbit in the so-called habitable zone, but because the star is dim, that zone lies much closer in than Earth does to the Sun. Close enough at a world there may be blasted by powerful flares, ultraviolet radiation, and streams of charged particles. In some systems, the star can be so active that it strips atmospheres away or bombards surfaces with conditions hostile to exposed life. So the galaxy may be full of planets that look promising at first glance, then turn dangerous when the parent star's temperament is revealed. This is why habitability is never just about distance. A world may sit in the right place for liquid water and still be punished by the very star that gives it light. Tidal locking might leave one side blazing and one frozen. On some planets, gravity can force an extraordinary kind of stillness. The world turns exactly once for every orbit, so the same hemisphere always faces the star that creates a permanent day side and a permanent night side. One half of the planet may endure constant starlight, while the other sits in endless darkness. At first, that sounds like the end of habitability. You imagine one side scorched and the other buried under ice. Yet reality may be more interesting. If the atmosphere is thick enough, or if oceans move heat efficiently, warmth could be redistributed around the globe. Instead of a simple split between hell and ice, there might be a ring of temperate conditions between extremes, a twilight belt, where life could survive under a never-changing sky. That is what makes these worlds so gripping. They seem easy to dismiss until climate physics steps in and says perhaps not. Alien habitability may depend on circulation, not symmetry. Alien sunsets might rise over worlds orbiting two suns at once. This is one of those cases where science fiction arrived first, and then the universe quietly admitted it was possible. Some planets orbit not one star, but a pair of them. These are circumbinary worlds, and their skies could be astonishing, depending on the stars' sizes, colors, and positions. A day might begin with two dawns or end with twin suns sinking together toward the horizon. Shadows could split seasons, and light cycles could become more complex than anything on Earth. But the wonder goes deeper than the image. These systems proved that planet formation is more flexible than many astronomers once thought. A young planet can survive the shifting gravity of two stars and settle into a long-term orbit around both. That alone is remarkable. It means worlds do not need simple, orderly systems to exist. Nature can build planets in dynamic, complicated environments, then keep them there for ages under skies that would look impossible to anyone raised beneath a single sun. Rogue planets may carry hidden notions through starless interstellar darkness. A planet without a star sounds doomed at first. No dawn, no sunlight, no seasons, just cold, endless night between the stars. Yet some scientists think such worlds might still protect liquid water beneath thick ice shells. The surface would be frozen hard, but below that frozen crust, heat from the planet's interior could linger for immense spans of time. A buried ocean might survive in total darkness, sealed away from the vacuum of space. That is an almost haunting image. A world cast out of its system, wandering alone through interstellar blackness, and yet still carrying an unseen sea inside it. If such places exist, they would broaden the map of possible habitats dramatically. Life would not need a shining sun overhead. It might persist in solitude, wrapped in ice, nourished only by internal warmth and chemistry in the deep. The galaxy's loneliest planets may not be dead, they may simply be hidden. Free-floating planets could keep life alive with internal heat alone. This idea pushes habitability to its most radical edge. If a planet is untethered to any star, then all the warmth that matters must come from within. Radioactive decay in the rocky interior, lingering heat from formation, and perhaps tidal interactions with moons could all help maintain energy over extraordinary lengths of time. On Earth, sunlight dominates the story of life at the surface. On a free-floating world, geology would have to take over that changes everything. The sky would give nothing. The ground below would become the only reliable source of warmth. It is possible to imagine deep environments where water remains liquid and chemistry remains active for billions of years, entirely independent of starlight. Such a biosphere would not resemble any familiar landscape. It would be inward-facing, hidden, and probably microscopic. Yet it would still count as life. That is the thrilling part. Biology may be able to survive not only far from stars, but completely without them. Some moons may be better homes for life than planets. That sounds backward at first, because planets seem like the obvious prize. They are larger, grander, and easier to imagine as homes. But some moons have qualities that make them especially intriguing. A moon can orbit a giant planet and still benefit from more than one source of energy. It may receive heat from radioactive elements inside, but also tidal heating from the constant gravitational flexing caused by its parent planet. That steady kneading can keep an interior warm drive geology and help maintain a hidden ocean for immense periods. In other words, a moon can stay active even far from the sun. Some may have more liquid water than Earth itself. Sealed beneath ice and protected from space above a planet in the habitable zone is still a compelling target. But the outer solar system taught us something profound. Life-friendly conditions may gather in small, overlooked places where gravity, ice, and internal heat quietly do the work of creating a habitat. Europa now appears to have carbon linked to its buried ocean. That discovery matters because carbon is not just another chemical, it is one of the central ingredients in the chemistry of life as we know it. Scientists had long suspected that Europa's hidden ocean could be promising, but one major question remained. Did that buried sea actually contain the right materials? Or was it mostly just water under ice? Observations from the James Webb Space Telescope gave the picture a sharper edge by identifying carbon dioxide on the surface in a region where it seems most likely to have come from the ocean below. In other words, material tied to the buried sea may have reached the surface and revealed part of its chemical story that does not prove biology, and it does not solve Europa's mystery. What it does is make the moon feel more complete. An ocean alone is exciting. An ocean with accessible signs of lip-related chemistry becomes a place that seems harder and harder to ignore. Enceladus appears to have phosphorus, a crucial ingredient for life. This discovery added another important piece to one of the most compelling astrobiology stories in the solar system. Phosphorus matters because it is central to biology on Earth. It helps build DNA, supports cell membranes, and plays a key role in energy transfer inside living systems. For a long time, scientists wondered whether Enceladus had enough of it in its hidden ocean. Then analysis of material from the moon's erupting plumes pointed to phosphorus in sulfuric ice grains flung into space. That is extraordinary because it means one of the classic biochemical ingredients may be present in a place already known for liquid water, organic compounds, and active chemistry. Enceladus keeps becoming less like an icy curiosity and more like a genuine environment. The moon is tiny, bright, and easy to underestimate. Yet beneath its frozen skin, it may hold a chemically rich ocean that checks more and more of the boxes scientists care about most. A living ocean may be easiest to find where ice cracks open. If an ocean lies hidden beneath miles of frozen crust, the greatest challenge is obvious. How do you reach it? Driving through that much ice on another world would be one of the hardest engineering tasks humans have ever attempted. So, scientists pay close attention to places where the ice is already weakened, fractured, or active. Cracks are not just scars. There may be natural windows into the ocean below. On Europa, long ridges and chaotic terrains suggest the surface has been shaped by movement from beneath. On Enceladus, the south polar fractures actively vent material into space. These broken regions are precious because they may bring hidden chemistry upward where instruments can inspect it. In astrobiology, access is everything. A world can be promising in theory and remain frustratingly silent in practice. But when the ice opens even a little, the ocean stops being only an idea. It becomes a place that can begin to answer back. Life elsewhere might feed on chemistry instead of sunlight. Earth trained us to associate life with daylight, leaves, and photosynthesis. Yet some of the most revealing ecosystems on our own planet do not depend on the sun at all. Their primary energy comes from chemical reactions. Microbes can harvest energy by oxidizing compounds such as hydrogen or sulfur, building living systems in darkness where no sunlight reaches. That possibility is crucial for the surge beyond Earth, because many of the most promising habitats are buried under ice or hidden deep underground. In such places, sunlight may never penetrate. If life exists there, it must run on chemistry. That is a profound shift in imagination. It means biology may not need a bright surface world with familiar weather. It may flourish in rock pores around hydrothermal systems, or within hidden oceans where molecules react and energy flows invisibly. The first extraterrestrial ecosystem may not be green or sunlight. It may be dark mineral-driven and perfectly content without a sunrise. Earth's deepest vents may show how alien ecosystems can begin far below the ocean surface, where sunlight never reaches. Hydrothermal vents pour hot mineral-rich fluids into black water. Around them, life gathers in abundance. Giant tube worms, pale crabs, clams, microbes, and whole food webs thrive there without relying on photosynthesis. That alone is astonishing, but the vents may tell an even deeper story. Some scientists think environments like these could resemble the kinds of settings where life first emerged on Earth. The rocks' heat, minerals, and chemical gradients create natural opportunities for complex chemistry to arise and organize. In other words, these seafloor systems may not only host life, they may hint at how lifeless chemistry turns into biology in the first place. That is why they matter so much for astrobiology. If hidden oceans on other worlds have rocky floors and active chemistry, then deep vents may not be an Earth-only curiosity. They may be one of the universe's favorite starting points. The first extraterrestrial life may be microbial, slow, and astonishingly ordinary. That expectation is important because popular imagination tends to race toward creatures' minds and civilizations. Science point somewhere much quieter. For most of Earth's history, life was microbial. Tiny cells ruled the planet long before animals, forests, or intelligence arrived. That suggests the first life we find elsewhere, if we find it at all, is far more likely to be microscopic than dramatic. It may form films on rock drift in buried water, or survive as sparse communities in harsh environments. To human eyes, it might seem almost disappointingly plain. Yet that would be one of the greatest discoveries in history. A few alien microbes would prove that biology is not unique to Earth. They would tell us that the universe can take chemistry and more than once turn it into living systems. The wonder lies not in size or spectacle. It lies in the crossing of that threshold. Even the humblest extraterrestrial cell would change humanity forever. Alien biospheres might bloom beneath ice. We have barely begun to probe. One of the most exciting possibilities in astrobiology is also one of the hardest to reach. Worlds with buried oceans may host entire living systems beneath frozen roofs, and we have hardly touched those environments at all. On Earth, thick ice once seemed like a barrier to life. Then scientists found thriving communities in subglacial lakes, sea ice, and other cold, hidden places. That lesson changed the way we look outward. Ice is not only a prison, it can also be a shield protecting liquid water below from radiation and impact damage above. Beneath it, an ecosystem might develop in darkness for immense spans of time. If that sounds speculative, it is because the worlds in question remain mostly inaccessible. We are still standing at the threshold, but that is what makes the idea so gripping. Entire alien biospheres may be there already, not exposed on surfaces for easy discovery, but sealed beneath crusts we have barely begun to understand. A plume from an icy moon could contain life's fingerprints. That possibility is what makes plume sampling one of the most elegant strategies in planetary science. Instead of landing, drilling, and somehow tunneling through a frozen shell, a spacecraft can fly through material that the moon has already expelled into space. If that spray comes from a subsurface ocean, then every ice grain and vapor particle becomes a messenger from the hidden environment below. Scientists can look for organic compounds, salts, isotopic patterns, and other signs that the ocean is chemically active in interesting ways. In the most thrilling scenario, the plume might even carry more subtle evidence, perhaps molecular combinations or textures that suggest biological processing rather than simple geology that would still require great caution. False positives are possible. Interpretation would be fierce, yet the principle is beautiful. A distant ocean world may not need to be cracked open by force. It may already be sending out samples of itself, waiting for us to notice what they mean. Mars once had lakes, rivers, and a far friendlier surface. The Mars we see today looks cold, dusty, and painfully still. But the planet keeps preserving evidence of another life chapter, entirely one, with flowing water, changing climates, and landscapes shaped by persistent movement. Ancient river channels snake across the surface deltas, spread out where streams once emptied into standing bodies of water. Sedimentary layers inside craters show that lakes did not appear for a single dramatic moment and vanish in some places. They filled, dried, and returned over long stretches of time. That matters because habitability is not just about having water. Once it is about having it long enough for chemistry to settle. Lemon do interesting work. Early Mars may have offered exactly that. A thicker atmosphere, milder conditions, and active water cycles would have made it feel less like a dead world and more like a planetary experiment. Interrupted halfway through that lost Mars is why the planet still grips us. Curiosity found ancient organics in mudstone from an old Martian lake. That discovery carried a special kind of tension because organic molecules are deeply important and not enough on their own. Curiosity drilled into ancient mudstone in Gale Crater, a place that once held a lake, and found preserved carbon-based compounds locked inside rock more than 3 billion years old. Mudstone is such a fascinating target because it forms from fine sediments settling in calm water. On Earth, that kind of environment can preserve chemical traces with remarkable patience. So when Curiosity sampled that old lake bed, it was not simply looking for interesting dirt. It was opening a chemical archive from a time when Mars was much wetter. The organics did not prove biology, but they did prove preservation. That is huge. It means ancient Martian rocks can still hold fragile clues after immense spans of time. Somewhere in that archive may be a deeper answer, waiting in material that has stayed buried and protected for billions of years. Martian methane seems to rise and fall in puzzling seasonal cycles. That is one of the strangest ongoing stories on the red planet. Methane is a simple gas, but it can have complicated origins on Earth. A great deal of it comes from living organisms, though geology can make it too. Curiosity detected changes in methane levels in the air near Gale Crater, with concentrations appearing to increase and decrease in a seasonal rhythm. That alone was enough to make scientists sit up. Why would the planet breathe in a pattern? Why would the gas seem to seep out then fade again? The obvious possibilities pull in very different directions. Perhaps subsurface rock and water are still reacting in ways that release methane today. Perhaps old gas is trapped underground and escapes when temperatures change. Or perhaps some unknown process is scrambling the signal entirely. The fascination comes from the behavior itself. Mars is not simply quiet. It seems to pulse chemically in ways we do not yet understand. Organic molecules on Mars do not prove life, but they matter. It is easy to hear the word organic and leap straight to biology. But in chemistry, that word simply means carbon-bearing compounds. And there are many ways to make them without life. Meteorites can deliver them geological reactions, can assemble them, radiation can alter and reshape them. So why does their presence on Mars matter so much? Because they are part of the vocabulary that life uses. They tell us that the planet has not been chemically barren. They show that potentially relevant ingredients existed there, assisted there, and in some cases survived inside ancient rock. That changes the story from empty to promising. A world does not need to reveal a fossil or a cell before it becomes interesting. Sometimes the first real sign is that the raw materials were present and that the environment did not destroy them all. Mars is compelling because it keeps showing that the chemistry of habitability was not absent. It was there, and traces remain. The best Martian fossils may still lie hidden underground. If life ever arose on Mars, the surface may be one of the worst places to look for its most delicate remains. Today, radiation from space strikes the exposed ground. Harsh oxidizing chemistry works away at vulnerable molecules. Winds move dust endlessly over immense spans of time. The surface becomes a difficult place for subtle evidence to survive. But underground, the story may be very different. Buried rock concealed ancient organics, preserve mineral textures, and protect old biosignatures from the slow erasing power of exposure. That is why drilling matters so much. A few centimeters below the surface is interesting. Meters below could be transformative. On Earth, some of the oldest traces of life survive in protected settings where minerals lock the evidence away. Early Mars may demand the same approach. Its most exciting archive may not be out in the open, but sealed below in sediments and fractures that have stayed hidden. Since the planet was young and wet, Venus once looked impossible, yet its clouds keep rejoining the conversation. For a long time, Venus seemed like the perfect warning against hopeful thinking. Its surface is hot enough to melt lead. The pressure is crushing. The atmosphere is thick, acidic, and deeply hostile. In that setting, life sounds absurd. Yet the conversation never entirely goes away because Venus has layers of cloud far above the inferno, where temperatures and pressures become much milder. Those cloud decks are still chemically extreme, but they sit in a range that tempts the imagination. Add to that the growing idea that ancient Venus may once have been far more Earth-like, perhaps with long-lived water in its past, and suddenly the planet becomes harder to dismiss. Not likely, not easy, but interesting. Again, Venus is compelling because it challenges the instinct to classify worlds too quickly. A planet can look utterly dead at first glance and reveal atmospheric regions and deep history that reopen questions people thought had been closed. Phosphine on Venus remains controversial, unresolved, and scientifically irresistible. Few recent planetary stories have swung so sharply between excitement and caution. When researchers announced a possible detection of phosphine in the clouds of Venus, the reaction was immediate. On Earth, phosphine is strongly associated with biology or industrial processes, so finding it on another planet would be extraordinary. But Venus is not Earth, and astronomy is unforgiving. Almost as soon as the result appeared, scientists challenged the data, the methods, and the interpretation. Some argued the signal was weaker than first, claimed others suggested sulfur compounds or instrumental issues could explain it. Follow-up studies have not settled the question cleanly, which is exactly why it remains so fascinating. The planet offered a hint, not a conclusion. And because the claim touched a molecule so provocative in astrobiology, it forced the whole community to examine Venus with fresh intensity. Sometimes the most powerful scientific event is not a discovery everyone accepts. It is a disputed one that refuses to go away. Even a false biosignature can teach us how to search better in a field this delicate. Mistakes are not just possible, they are productive. A world may produce an intriguing signal that looks exciting at first, only for scientists to discover that geology, sunlight, chemistry, or instrumental quirks can imitate it. That may sound disappointing, but it is one of the ways the search becomes sharper. Every false biosignature teaches researchers which assumptions were too simple and which planetary environments can fool them. It forces better models, more careful observations, and more demanding standards of proof. In other words, it raises the quality of the search. A misleading signal can reveal just how creative planets are without life. That matters because the universe is not obliged to make this easy. He can produce oxygen without forests, methane without microbes, and strange atmospheres with no biology involved at all. Learning those lessons in advance is essential. The road to a real detection may be paved with signals that turned out not to mean what we hoped. Life detection is hardest when chemistry can imitate biology. That is the central challenge in astrobiology. Life changes its environment, but so does non-living chemistry. A gas in an atmosphere may look suggestive until scientists realize volcanoes, sunlight, rock interactions, or photochemical reactions could make the same thing. A planet may seem rich in possibility, then reveal the perfectly natural explanation that strips the mystery away. This is why the field demands patience. One signal alone is rarely enough. Researchers need context combinations and patterns that become harder and harder to explain without biology. It is not enough to ask, whether something interesting is present. The real question is whether nature without life could have made it just as well. That is a much tougher standard and righty. So the difficulty is what keeps the field honest. Detecting life from across interstellar distances was never going to be simple. The hardest part is not seeing something unusual. It is proving that unusual really means alive. Scientists must ask what else could make the same signal. That habit of skepticism is not a barrier to discovery. It is the only path to one that will last. Whenever an atmosphere, plume, or spectrum shows something intriguing, the first task is not celebration. It is elimination. Could the signal come from geology, from radiation from surface minerals, from measurement bias, from contamination closer to home? In a field where the stakes are immense, every alternative explanation must be dragged into the light and tested hard. This discipline can seem almost cold, especially when the public wants wonder immediately, but it is what protects the final answer. A genuine biosignature must survive repeated attempts to explain it away. That is why the search moves carefully, not because scientists lack imagination, but because they have enough imagination to know how many non-living tricks a planet can play before humanity can say we found life. Researchers must be able to say they looked for every other answer first and failed to make it fit. Oxygen alone would not be enough to declare alien life on Earth. Oxygen feels deeply biological because photosynthetic life transformed our atmosphere with it. That makes it tempting to treat oxygen as a universal sign of living worlds. But planets are more complicated than that. Under certain conditions, some night can spurt water molecules and allow hydrogen to escape into space, leaving oxygen behind without any organisms involved. Other atmospheric processes may also build up oxygen in ways that imitate a biosphere. So if astronomers detect oxygen on an exoplanet, the result would be exciting, but not definitive. They would immediately want to know what kind of star the planet orbits, how much water it may have lost, what other gases are present, and whether the world's chemistry supports a non-living explanation. This is part of what makes astrobiology so subtle. A molecule that seems almost like a shout can turn into only a clue. Oxygen matters enormously, but by itself, it cannot yet carry the full burden of proof. Methane becomes far more exciting when it appears in the right company. Methane alone is intriguing. Methane with the right companions becomes much harder to ignore. On a living world, the most interesting signals may come not from single gases, but from combinations that should not remain stable together for long. If methane and oxygen both persist in large amounts, for example, something must keep renewing them because they tend to react away over time. That kind of atmospheric tension is exactly what scientists love. It hints that a planet is not chemically at rest. Something is actively maintaining the imbalance that something could still be geology depending on the world. But the more constrained the environment becomes, the more suggestive the combination may be. This is why biosignatures are often discussed as ensembles rather than isolated molecules. The atmosphere must be read like a conversation, not a single word. Methane becomes more compelling when the rest of the planetary story makes it difficult for ordinary chemistry to explain away. Biosignatures depend on planetary context as much as the molecules themselves. The same gas can mean very different things on different worlds. That is why palmatory context is everything. A molecule does not arrive with a label explaining how it formed. Scientists have to infer its origin by understanding the star, the atmosphere, the surface, the climate, and the likely chemistry of the entire system. Carbon dioxide on one planet may be ordinary on another. Paired with methane and the absence of ammonia, it may suggest something far more interesting. Oxygen around a quiet star could mean one thing around an intensely active star. With a history of water loss, it might mean something else entirely. In this way, life detection becomes less like finding a single magical clue and more like solving a layered mystery. The atmosphere is only one chapter. To read it properly, you need the whole book. Without context, even a promising world can be misunderstood. With its subtle patterns begin to acquire real meaning. A living world may reveal itself through atmospheric imbalance. Planets left to themselves tend to drift toward chemical stability. Reactions happen, energy spreads out, and atmospheric mixtures settle into states that ordinary physics and chemistry allow. Life disrupts that calm. It consumes certain molecules, releases others, and keeps a world from resting where it otherwise might. Earth is a superb example. Our atmosphere is not just a passive sky. It is a system constantly altered by biology. That idea lies at the heart of many biosignature strategies. Scientists are not simply searching for familiar gases. They're looking for evidence that a planet is being continuously pushed away from chemical equilibrium. That kind of imbalance can be a profound clue. It suggests metabolism on a planetary scale, even if the organisms involved are tiny. The beauty of this approach is that it does not require alien life to look like Earth life in detail. It only requires that life, whatever its form, leaves a detectable restlessness in the air. Seasonal gases on a distant planet would make scientists sit up straight. Seasons imply rhythm, and rhythm can be a powerful clue. On Earth, the atmosphere changes over the year because living systems respond to light, temperature, growth cycles, and decay. Forests inhale and exhale in broad seasonal pulses. Microbes and oceans contribute their own variations. If astronomers were ever able to detect recurring seasonal shifts in a distant atmosphere, especially in gases tied to biological or surface activity, it would be electrifying. Not because it would prove life instantly, but because it would suggest the planet is dynamic in a patterned way. A one-time detection can always be questioned. A repeating cycle invites a deeper story. Perhaps the planet has changing weather, freezing and thawing surfaces, or chemical processes that rise and fall predictably. Perhaps something more interesting is involved. Either way, seasonality would turn a distant world from a static object into a living system of processes, unfolding over time, and that would change how we look at it. Pigments from alien life could change the color of a planet. Life does not only breathe and metabolize, it also captures light. On Earth, photosynthetic organisms alter the way our planet reflects sunlight, and those effects can be measured from afar. That raises a thrilling possibility. Alien biology might use pigments unlike chlorophyll, tuned to a different star and a different environment, yet still change the visible character of a world. A planet could show a surface color or reflectance pattern that makes little sense geologically, but fits the idea of widespread light harvesting. Life under a red dwarf star, for example, photosynthetic organisms might evolve different strategies than plants on Earth. Their world could look darker, stranger, or shifted in ways we do not instinctively expect. This is one reason exoplanet science feels so imaginative and rigorous at the same time. Researchers are asking whether a living surface might advertise itself, not through cities or signals, but through color. The skin of a planet may one day hint at biology from across the stars. Even alien oceans might leave clues in reflected starlight. An ocean does not need to be directly seen to affect what a planet looks like from afar. Large bodies of liquid can influence brightness, polarization, and the way light changes as the planet rotates or moves through its phases. Under the right circumstances, a smooth liquid surface can produce a kind of glint, a bright flash of reflected starlight that hints at something vast and fluid below the clouds. That possibility is deeply exciting because oceans matter so much to habitability. They regulate climate, store heat, dissolve chemicals, and provide environments where life may begin or thrive. So if astronomers can infer the presence of surface liquid from light alone, they gain much more than a scenic detail. They gain evidence that a planet may have one of the most important ingredients in the whole story. A distant world might never show us its waves directly, yet still betray their existence through a shimmer crossing the face of the planet. Clouds can hide a world's secrets better than distance can. People often assume that the main obstacle in studying exoplanets is how far away they are. Distance is difficult, but clouds can be even more frustrating. A thick cloud layer can mask the lower atmosphere, blur spectral signals, and conceal the very processes scientists most want to study. Venus is the classic lesson close to home. Its bright, beautiful cloud deck hides an inferno below. On exoplanets, clouds and hazes can do the same kind of mischief, muting the fingerprints of gases and making interpretation vastly harder. A world may sit in a promising orbit with a suggestive size and an interesting atmosphere, yet remain stubbornly unreadable because the upper layers refuse to let us see deeper. That is why clouds are so important in the search for life. They do not merely decorate a planet, they control what we can know about it. Sometimes the greatest mystery is not far away, it is right there in the sky. The wrong atmosphere can make a promising world suddenly less alive. A planet can look wonderful on paper until its atmosphere enters the conversation. A location in the habitable zone sounds promising. A rocky size sounds promising. Even hints of water can sound promising. But if the atmosphere is too thin, liquid water may not survive. If it is too thick, the surface may become crushing or overheated. If it lacks key gases, temperature swings may be brutal. If radiation from the star has stripped it away, the surface may be left exposed and hostile. In astrobiology, the atmosphere is not background scenery. It is the system that determines whether the rest of the picture can hold together. This is why so many once exciting worlds become more uncertain as scientists learn more about them. Hope is easy early on. Habitability gets harder as details arrive. The atmosphere can rescue a planet or ruin it. A promising world does not stay promising automatically. Its air has to earn the optimism. The search for life is really a search for patterns. That may be the most elegant way to understand the whole field. Scientists are not waiting for a tiny alien waving through a telescope. They're looking for repeating structures in data, combinations of molecules, rhythms in atmospheres, chemical imbalances, surface colors, plume contents, and clues that make more sense together than apart. One measurement can excite, a pattern can persuade. Life is powerful because it tends to organize matter and energy in distinctive ways across time. It builds persistence where chemistry alone might fade. It creates linked signals rather than isolated ones. So the search becomes an exercise in reading planetary behavior. Does this world have a stable atmosphere that should not be stable? Do these gases belong together? Does this signal recur? Does this surface reflect light in a strange but coherent way? In the end, that is what makes the hunt so fascinating. We are searching not just for substances, but for order written into worlds from very far away games. Webb is already testing atmospheres for signs of habitability. For decades, the search for life beyond Earth lived partly in the realm of future promises. Then the James Webb Space Telescope began examining real alien atmospheres with a level of precision that once sounded almost impossible. This is what makes the moment feel historic. We are no longer only listing interesting planets and hoping someday to study them properly. We are beginning to test what their skies are made of. Webb can look for gases tied to climate, water, and chemistry that may shape whether a world could support life. It is not yet reading alien weather reports line by line, and it is not handing us proof of biology. But it is turning distant planets into physical places with measurable air that shift matters deeply. A candidate world stops being a hopeful dot and starts becoming an environment. For the first time, humanity has an instrument that can truly begin interrogating the atmospheres of other worlds. Webb can study alien air by watching starlight filter through it. The method is as elegant as it is astonishing. When a planet passes in front of its star, a tiny portion of the starlight slips through the planet's atmosphere before reaching our telescopes. That atmospheric rim may be only a thin veil, but it leaves fingerprints in the light. Different gases block different wavelengths, so the starlight arrives subtly altered. Webb can measure those changes and infer what molecules are present. It is an almost unbelievable feat. A telescope floating far from Earth can detect signs of water vapor, methane, carbon dioxide, and other compounds in air wrapped around the world like years away. Nothing about this is visually dramatic. There is no glowing alien skyline. There is only exquisite measurement and patient interpretation. Yet the result feels magical. Anyway, We are reading the chemistry of distant skies without ever going there through filtered starlight alone. Planets that once seemed utterly unreachable begin to tell us what fills the air above them. Future telescopes may spot Earth-like worlds by blocking their stars. One of the great challenges in exoplanet astronomy is that stars are overwhelming. A planet like Earth is tiny and faint beside the brilliance of the star it orbits in visible light. It is like trying to see a firefly beside a searchlight from an unimaginable distance. That is why future observatories may rely on a bold trick. They will try to suppress the starlight itself by using advanced chronographs inside the telescope, or perhaps even separate star shades flying in formation. Astronomers hope to block the star's glare and reveal the much dimmer planet nearby. If that works well enough, the payoff would be enormous. Scientists could directly study small rocky worlds and analyze the reflected light from their surfaces and atmospheres. That means oceans, cloud seasons, and perhaps biosignatures could become far easier to investigate. The star has always dominated the scene. These future missions aim to dim the spotlight so the most interesting world in the picture can finally emerge. The next great life detector may listen, not look, for all the power of telescopes. Some discoveries may arrive through listening rather than seeing. That possibility has always given the search for extraterrestrial life a different emotional texture. A visible biosignature suggests life that exists. A signal suggests life that knows enough to transmit intentionally or not. Radio, astronomy, optical searches for brief laser flashes, and other forms of signal hunting are all built on the idea that intelligence may be more detectable through technology than through biology alone. This is a thrilling reversal. A microbial world can change its atmosphere, but a technological civilization might reshape the sky with patterns no ordinary planet would produce. Listening has another advantage. Signals can cross enormous distances. They do not require us to resolve continents or clouds. They only require a sender and a receiver occupying the same cosmic moment. That is why the next major breakthrough may not be a new image. It may be something far stranger, a pattern in the noise. SETI searches the sky for intelligence hiding inside radio noise. That sentence captures the strange beauty of the enterprise. The search for extraterrestrial intelligence is not mostly about giant traumatic moments. It is about combing through torrents of radio data, trying to distinguish natural cosmic emissions, human interference, and the possibility of something artificial. Space is loud in its own way. Pulsars flash, galaxies murmur, stars crackle, and Earth itself contaminates observations with a flood of technological clutter. Inside all of that, SETI researchers look for signals with unusual properties, narrow bandwidths, persistent frequencies, or patterns that stand apart from the messy habits of nature. It is detective work on the cosmic scale. Most of the time, nothing survives scrutiny, but the search remains compelling because it only takes one extraordinary exception. A single credible artificial signal would transform human history. So the work continues, patient and methodical, with scientists listening through the noise of the universe for any hint that somewhere someone else has also learned how to speak with radio. Technosignatures could include lasers, pollution, or impossible amounts of heat. When people imagine alien technology, they often jump straight to radio messages, but technosignatures can be far broader than that. Any large-scale activity by an advanced civilization might leave a detectable mark if it changes a planet or its surroundings in an unusual way. Powerful lasers could flash across interstellar distances as communication beacons or energy systems. Atmospheric pollution from industry could build up in combinations that are difficult to explain through geology alone. Excess infrared heat might reveal massive energy use, perhaps from planetary engineering or large structures intercepting starlight. The beauty of this idea is that it does not depend on aliens trying to contact us directly. A civilization may simply be busy, and its byproducts may leak into space. That turns the search into something wonderfully expansive. Scientists are not only waiting for a greeting, they are watching for evidence that intelligence anywhere has become powerful enough to leave fingerprints. On a planetary or stellar scale, an alien civilization might be easier to detect than alien bacteria. That sounds counterintuitive, but in some cases, it may be true. Microbes can be abundant and world-changing, yet their signals may still be subtle, tangled up with geology, climate, and chemistry. A technological civilization, by contrast, could generate unmistakably artificial patterns. A focused radio transmission, an engineered light source, or a planet whose atmosphere contains improbable industrial compounds may stand out more clearly than the faint metabolic traces of a simple way-a biosphere. This creates an odd and fascinating possibility. The first sign of life beyond Earth might not come from the most common life at all. It might come from the rarest, the kind that builds tools, alters its environment deliberately, and leaves large-scale evidence behind. Of course, civilizations may also be scarce, brief, or silent, which complicates the picture immensely. Still, the logic remains striking. The universe's simplest life may be hardest to prove. While a sufficiently active intelligence could accidentally make itself obvious across interstellar space, intelligent life may reveal itself by changing a planet on purpose. That possibility adds intention to the whole search. Biology changes a world simply by existing, but intelligence can go further. It can choose to alter landscapes, engineer climates, produce new chemicals, and build systems that would never arise naturally. If such changes are large enough, they may become detectable from far away. A civilization might brighten the night side of its world, fill its atmosphere with unusual synthetic gases, or generate heat signatures that far exceed what ordinary planetary processes should allow. More speculative possibilities reach even further toward orbital structures or deliberate beacons meant to announce presence across the dark. What matters most is the principle. Purpose leaves a different kind of mark than metabolism. It introduces patterns shaped not just by survival, but by planning and design. That is why technosignatures are so compelling. They shift the question from whether life exists to whether any life out there has become capable of treating its whole planet as a project. We now search for artificial light on distant worlds. That idea feels almost poetic. For most of history, city lights were symbols of human civilization, seen from nearby, not something to imagine across interstellar distances. Yet astronomers have seriously considered whether artificial illumination on the night side of an exoplanet could one day become detectable. The challenge is enormous. Natural reflected starlight, atmospheric effect, and sheer distance make the problem brutally difficult. But as telescopes improve, the concept remains scientifically meaningful. Artificial light would behave differently from sunlight. It could produce unusual brightness patterns as a planet rotates, especially if illumination is concentrated in regions rather than spread naturally. What makes the idea so captivating is how intimate it feels. Atmospheric gas is a grand planetary clue, but lights suggest inhabited places. They hint at settlements, routines, and waking beings on the far side of a world. We are nowhere near making such detections with confidence today. Still, the search is already widened enough to imagine seeing not just worlds, but the glow of activity on them. We also search for chemicals that industry could leave behind. Some molecules are rare or unstable in ways that make them especially interesting if found in abundance on Earth. Modern industry has filled the atmosphere with compounds that nature does not usually produce in large quantities. That raises a thrilling possibility for exoplanet science. A distant civilization might alter its atmosphere with synthetic chemicals, and those compounds could become detectable as technosignatures if they are distinctive enough. Scientists sometimes discuss molecules similar in spirit to industrial refrigerants or other manufactured substances because they would be difficult to explain through ordinary planetary chemistry. In a sense, that means pollution could become evidence of intelligence. It is a strange and slightly sobering thought. The side effects of technology may travel farther than the civilization intended. If so, one of the clearest signs of alien industry might not be a monument, a signal, or a spacecraft. It might be the atmospheric residue of a world that became technologically active and changed its own sky. A powerful narrow-band radio signal would be hard to ignore. Nature usually spreads radio energy across broad ranges of frequency. A very narrow-band signal, tightly confined and persistent in a way ordinary astrophysical sources rarely produce, would immediately attract attention. That is one reason SETI has long cared about this kind of pattern. It looks engineered, not proof by itself, certainly, but enough to trigger serious scrutiny. Astronomers would ask whether the signal drifted in a way consistent with a source on a rotating planet. They would check if it repeated, whether other observatories could see it, and whether human technology might be to blame. The fascination comes from how little imagination would be needed in that moment. A signal like that would not feel like a vague atmospheric hint. It would feel like a deliberate structure emerging from the noise. That is why narrow-band detections carry such emotional power in public imagination. They resemble communication more than chemistry. If one ever arrived cleanly and repeatedly, the world would stop and listen. The wow signal appeared once, then never returned. That single fact is why it still lingers in the imagination with such strange force. In 1977, a radio telescope at Ohio State University recorded an unusually strong narrow-band signal lasting about 72 seconds. The astronomer reviewing the printout circled it and wrote "wow" in the margin, giving the event its famous name. Then the signal vanished. It never reappeared in a way that could confirm it. That disappearance is everything. If it had repeated, this story might already have transformed astronomy. If it had been clearly explained, it would have faded into a historical footnote. Instead, it hangs in the uneasy space between those outcomes, too striking to forget, too brief to trust. Over the years, many natural and human-made explanations have been proposed, but none has buried the mystery cleanly enough to satisfy everyone. The signal became legendary, not because it solved anything, but because it offered a glimpse of possibility and then withdrew it fast. Radio bursts once sounded alien, then grew stranger in another way. When these eruptions were first discovered, they seemed almost absurd. Enormous bursts of radio energy flashed across the sky for mere milliseconds, then disappeared. They were so brief and so powerful that speculation naturally ran wild. Some people wondered whether they could be artificial, perhaps signs of vast engineered systems or some unknown technological process. That excitement did not last in its original form, but the story did not become dull. It became richer as more bursts were found. Astronomers learned that they came from distant galaxies, and that some repeated in ways that hinted at extreme astrophysical engines rather than transmitters. The universe had not delivered evidence of alien communication. It had delivered something else, just as startling, a new class of violent cosmic phenomenon that challenged existing models. This is one of astronomy's most revealing habits. The sky often offers a mystery that feels almost designed, then turns out to be natural in a way even more astonishing. Some repeating bursts now seem linked to violent dead stars. That connection is one of the leading ideas in the effort to explain at least part of the fast radio burst puzzle. Many astronomers suspect that some of these signals are produced by magnetars, which are the immensely dense remains of dead stars with magnetic fields so strong they stretch human intuition to breaking point. A magnetar is not just a collapsed object, it is an extreme engine of stress capable of star quakes, energy outbursts, and violent interactions with surrounding matter. If one of these objects releases energy in the right way, it may produce an intense radio flash visible across cosmic distances. That explanation is both satisfying and eerie. A mystery once tempting to attribute to intelligence may instead come from stellar corpses under impossible magnetic strain. The universe, as usual, turned out not to be less dramatic than the speculative explanation. It was more dramatic. Repeating bursts may be the cries of dead stars, still capable of astonishing violence, long after their original suns are gone. One dramatic radio burst turned out to be human space junk. That revelation was a perfect reminder of how carefully astronomers must think before assigning cosmic meaning to a strange signal. For a brief moment, an unusual radio event appeared to come from deep space. It was dramatic enough to invite speculation, and like many such detections, it carried that electric feeling of possibility. Then the mundane culprit emerged. The source was not an alien transmission or some new astrophysical phenomenon, but a dead satellite much closer to home. In a way, that answer is almost comical, yet it is also deeply instructive. Earth is surrounded by technology, debris reflections and interference, all of which can creep into observations and masquerade as something far grander. This is why false alarms are unavoidable in the search for life and intelligence. Our own civilization throws noise into the sky before we can hear another one. Clearly, we have to learn how to stop hearing ourselves in everything. The universe keeps producing signals that feel designed for mystery. This is part of what makes astronomy so addictive. Again and again, the sky offers events that seem almost theatrically strange. A burst appears once and never returns. A signal repeats from a distant galaxy in a baffling rhythm. A spectrum hints at a provocative molecule, then becomes contested under closer inspection. These episodes are rarely simple, and that is exactly the point. The universe does not behave like a neat puzzle book with one clue leading cleanly to one answer. It behaves like a place full of layered phenomena, where rarity, distance, noise, and incomplete information conspire to create ambiguity. For anyone drawn to the question of life beyond Earth, that ambiguity can be maddening, yet it is also part of the charm. The cosmos keeps inviting interpretation, then resisting it. It produces signals that seem almost narratively perfect, as if designed to provoke wonder, skepticism, and hope, all at once before slipping back into uncertainty. False alarms are part of the story, not failures in a search. This difficult false alarms are not embarrassing detours, they are built into the process. Every time astronomers chase a strange signal, test a bold claim, or rule out an exciting interpretation, the field becomes stronger, instruments improve, data analysis sharpens. Researchers learn which kinds of interference recur, which natural phenomena can mimic artificial ones, and which assumptions need to be retired. That means the story of searching is not a simple sequence of triumphs. It is a long education in being fooled less often. There is something noble in that science does not progress by avoiding error. It progresses by exposing it, studying it, and becoming harder to deceive. So when the candidate techno-signature collapses under scrutiny, it is not wasted effort. It is rehearsal for the real thing. The first convincing detection of alien intelligence, if it ever comes, will stand on a mountain of earlier moments when scientists thought, maybe, then discovered exactly. Why not? Every unexplained signal teaches astronomers how not to fool themselves. That lesson may be one of the most valuable products of the whole enterprise. Each puzzling detection forces researchers to ask harder questions. Was the telescope behaving perfectly? Could the processing pipeline introduce artifacts? Is there interference from aircraft, satellites, or ground-based electronics? Can the event be repeated? Can another observatory confirm it independently? Those habits of suspicion are not obstacles to wonder. They are what make wonder durable when it finally survives. An unexplained signal, even one meter dismissed, leaves behind a trail of practical wisdom. It teaches astronomers where blind spots hide. It reveals which kinds of data are misleading, which frequencies are especially messy, and which methods are too trusting. In that sense, every mystery improves the search, even when it ends with an ordinary answer. The field grows not only from discoveries, but from disciplined disappointment. Before humanity can recognize a genuine sign of another intelligence, we have to become experts at ruling out ghosts. Some searches now coordinate radio telescopes across the planet. That coordination matters because a single telescope can be fooled in too many ways. Local interference, equipment glitches, and brief one-off events can all mimic something extraordinary. But if multiple observatories, separated by huge distances, observe the same candidate's signal at the same time, the case becomes much stronger. This is why modern SETI efforts increasingly emphasize coordination. Telescopes on different continents can watch the same target, compare detections, and immediately test whether a signal is local noise or something truly celestial. It turns the search into a global act of listening. There is something deeply moving about that. Image dishes and antennas spread across Earth, all focused on the same patch of sky, trying together to decide whether something unusual is really there. It is also scientifically powerful. Coordination raises the standard of evidence and narrows the room for confusion. If a serious candidate ever appears, the planet may need to verify together almost immediately. The dream of first contact often begins as data cleaning that may be the most realistic and charmingly unglamorous truth in the entire search. Popular imagination goes straight to a signal arriving in dramatic clarity while scientists sit stunned before a screen. Real life is usually messier. Before anything extraordinary can be claimed, oceans of raw data must be cleaned, filtered, sorted, and stripped of interference. Software flags patterns, analysts remove contamination from satellites, aircraft, terrestrial electronics, and instrument artifacts. The work can feel almost dull from the outside, yet this is where first contact would most likely begin. Not with a booming cosmic message, but with an anomaly that survives one practical test after another. That process is beautiful in its own way. It means the path to one of humanity's biggest discoveries may run through patience, discipline, and mundane technical work. The first true sign of another intelligence would not bypass science. It would emerge from it one careful layer of clean data at a time. Habitable does not mean inhabited, and that distinction changes everything. A world can have the right temperature, the right chemistry, and even liquid water, yet still be empty. That is one of the most sobering ideas in astrobiology. Habitability describes opportunity, not outcome. It tells us a planet may allow life, but it says nothing about whether life ever began there or whether it lasted on Earth. Life took hold astonishingly early, which tempts us to think it may bloom wherever conditions allow. But we do not know that the leap from chemistry to biology may be easy, or it may be one of the rarest events in the universe. That is why this distinction matters so much. A habitable planet is not a discovery of life. It is a doorway standing open. Whether anything ever walked through that doorway is a different question entirely. The galaxy may be full of beautiful water, bearing life-friendly worlds that remained forever silent, or it may not. We simply do not know yet. A perfect temperature means little without the right atmosphere. Temperature sounds simple when people talk about habitable worlds, but it can be deeply misleading. A planet may orbit at just the right distance from its star and still be hopeless for life if its atmosphere is wrong. Air is not decoration. It is the regulator, the shield, and often the difference between a stable environment and a ruined one. Without enough atmosphere, liquid water may vanish quickly, boiling away in daylight or freezing hard at night. With too much of the wrong kind, a planet can become a furnace. Venus is the great lesson here. It orbits closer to the sun than Earth. Yet the real story is not only the distance, it is the atmosphere that traps heat so efficiently that the surface becomes devastatingly hot. This is why astronomers care so much about alien skies. A planet's temperature on paper may sound promising. The atmosphere decides whether that promise means anything at all. Too much water might make a world less Earth-like, not more. At first, a planet covered in water sounds like the dream. Water is life's most celebrated ingredient, so more of it seems automatically better. But a world with too much water may become something very different from Earth, and not always in a helpful way. Continents on our planet do important work. They drive weathering, recycle nutrients, and interact with the atmosphere in ways that help stabilize climate over long spans of time. Remove them, and the whole system changes. A deep global ocean may isolate the water from the rocky interior beneath, especially if high-pressure ice forms far below the surface. That separation could limit access to the minerals and chemical exchanges, but many scientists think are important for life. An all-ocean world might still be habitable, perhaps beautifully, but it might also be biologically constrained in ways Earth is not. More water does not automatically mean more Earth-like. It may mean stranger, deeper, and harder. A planet can sit in the habitable zone and still fail. The habitable zone is a useful idea, but it is not a verdict. It simply marks the range around a star where liquid water could exist at the surface under the right conditions. Those last words matter enormously. A planet in that zone may still lose its atmosphere, freeze into a global ice state, overheat under thick clouds of greenhouse gas, or suffer constant radiation from a violent star. It may never have had enough water to begin with. It may have had too much. It may have formed in ways that left it geologically dead, with no magnetic field and no long-term climate stability. In other words, sitting in the right orbital range is more like being invited to the game than winning it. The phrase habitable zone can sound comforting, almost definitive. In reality, it is only the start of a much harder conversation. Plenty of worlds may occupy that sweet spot and still miss the conditions life truly needs. Red dwarfs offer many targets and many reasons for caution. These small stars dominate the galaxy by sheer numbers, which makes them irresistible to anyone searching for life. If most stars are red dwarfs, then many potentially habitable planets are likely to orbit them. That means red dwarfs may host a huge share of the real estate in the cosmic search, but they come with problems. Their habitable zones sit close in, which exposes planets to stronger flares, harsher radiation, and tidal locking. Young red dwarfs can be especially unruly, blasting nearby worlds during critical early stages when atmospheres may be vulnerable. Yet they also live for astonishingly long times, far longer than stars like the Sun. That longevity could, in principle, give life vast stretches of time to emerge and evolve. So red dwarfs are both hopeful and troublesome. They may be the galaxy's most common hosts for life, or some of its most disappointing traps. Either way, they cannot be ignored. They are too numerous to overlook and too complicated to trust easily. A thick atmosphere can save life or suffocate its chances. Atmospheres are not simple blessings. Their value depends on their composition, pressure, and history. A thick atmosphere can be a marvelous protector. It can trap warmth on a cold world, spread heat from one hemisphere to another, block harmful radiation, and allow liquid water to persist where it otherwise could not. But that same thickness can become catastrophic if the chemistry is wrong. A heavy greenhouse blanket can drive temperatures to unlivable extremes. Crushing surface pressure can alter the physics of water and make an environment hostile to familiar biology. Clouds may conceal the surface beneath conditions that are anything but mild. This is one reason exoplanets are so fascinating. The same broad feature can mean opposite things depending on the details. A dense atmosphere might rescue a marginal world from freezing, or it might turn a promising planet into a sealed pressure cooker. In astrobiology, almost every comforting idea has a shadow. Air can preserve life, and it can ruin it. Subsurface oceans may outnumber warm Earth like surfaces across the galaxy. This possibility is one of the great mental shifts in modern astrobiology. For a long time, people imagined life-bearing worlds mainly as Earth-like planets with blue skies, open seas, and temperate surfaces. But the solar system itself began to challenge that picture. Europa Enceladus and other icy worlds suggest that oceans can exist hidden under thick crusts of ice, kept liquid by internal heat rather than direct sunlight. If that can happen here, it may happen all over the galaxy. Buried oceans could be common on moons, dwarf planets, and free-floating worlds far from any star. That means the most abundant habitable environments may not be sunlit surfaces at all. They may be dark internal seas, invisible to most telescopes, sealed beneath frozen roofs. Such places would not look welcoming to human eyes, but life does not need beauty in the way humans define it. The galaxy's most common watery habitats may be hidden worlds that never see a sunrise. The most common living worlds might be dark, buried, and hidden. That idea turns the usual image of alien life almost upside down. Popular imagination favors open landscapes beneath alien skies, but nature may prefer secrecy. A buried ocean under ice has several advantages. It is shielded from radiation. It is protected from impacts. It can remain stable for immense spans of time if internal energy continues to flow. Those are not trivial advantages. They may make hidden habitats more durable than exposed surfaces, especially around restless stars. If life only needs liquid water, chemistry, and time, then dark internal worlds may be excellent homes. The most common inhabited places in the universe might never reveal mountains, continents, or clouds to any distant observer. They may be enclosed seas under frozen shells, with ecosystems built around hydrothermal chemistry in eternal night. That is a haunting thought. The galaxy could be alive in many places, yet most of that life may exist in environments so concealed that from the outside they appear silent, frozen, and utterly empty. Alien life may thrive where no telescope can ever see it. This is one of the humbling limits of the search. Telescopes are magnificent, but they mostly read surfaces, atmospheres, and light. If life flourishes under kilometers of ice, deep in rock, or beneath opaque cloud layers, then many of its habitats may remain hidden from even our finest instruments. A world could be biologically rich and still look blank from afar. That possibility matters because it means silence in our data does not necessarily mean silence in reality. We are searching with tools that are superb, yet some questions are nearly blind to others. The universe may contain living systems that do not advertise themselves in any way we can currently detect. That is not a failure of life. It is a reminder of the kind of habitats nature may favor. We often imagine discovery as a matter of building bigger telescopes. In some cases, the real problem is that the most interesting biology may be physically sealed away from view. We may first know life exists long before we know its shape. That is a beautifully strange prospect. The earliest evidence of alien life may come not as a creature or image, but as an inference. A planet's atmosphere may show a pattern that strongly suggests biology. A plume may contain molecules that point toward metabolism. A chemical imbalance may become so persistent and so difficult to explain that the conclusion begins to harden. And yet even then, we may still have no idea what the life actually looks like. No faces, no bodies, no movement across a visible surface. Just evidence. That is a very likely path to discovery, and it is worth dwelling on because it separates existence from appearance. Humanity may learn that the universe is alive before it learns whether alien life resembles microbes, mats, drifting cells, or something stranger. The first answer may come in abstract form. We may know there is life out there while remaining completely ignorant of its form, texture, and beauty for a long time afterward. Life elsewhere might never use oxygen, chlorophyll, or sunlight at all. Earth tempts us to treat its solutions as universal, but they may be only one version among many. Oxygen transformed our world. Chlorophyll powers much of our surface biosphere, and sunlight drives a huge share of life here. Yet none of those things may be mandatory. Early Earth lived without oxygen for a very long time. Microbial communities today still thrive in places where sunlight never reaches different stars. Amid different kinds of light and alien biochemistry may evolve pigments unlike anything on our planet. Some worlds may rely on chemical energy from rocks and water rather than photosynthesis. Others may use metabolic pathways that never generate oxygen at all. This matters because the search can become too Earth-centered. If we are not careful, a world lacking familiar signs might still be biologically active in ways we barely anticipate. The universe may host life that is truly alive, deeply successful, and completely unfamiliar in the basic machinery it uses to survive. The universe may prefer microbes over minds. Almost everywhere on Earth, microbial life arrived early and dominated for most of planetary history. Complex animals, plants, and intelligence came much later, and only after a vast amount of time and contingency. That suggests something important. The easiest kind of life to emerge and persist may be simple life. A universe full of microbes and nearly empty of minds is not only possible, it may be the most likely outcome. That idea can feel disappointing at first, until you realize how extraordinary microbial life already is. A single alien microbe would prove that biology is not unique to Earth. Entire microbial biospheres could transform oceans, atmospheres, and crusts without ever producing anything like a civilization. If that is the common case, then the galaxy may be biologically rich while remaining technologically quiet. It may teem with metabolism, adaptation, and evolution at small scales, yet rarely cross into intelligence. Life may be common, but minds like ours may be the unusual flourish, not the rule. Complex life could be rare, even if simple life is common. That possibility follows naturally from what Earth seems to teach. Single-celled life may arise relatively easily under the right conditions, but complex multicellular organisms appear to require a long chain of additional developments. Stable environments, energetic metabolisms, evolutionary innovations, and perhaps a great deal of luck may all be involved on our own planet. Complex life took billions of years to appear. That is not a quake or inevitable transition. So a galaxy full of living worlds might still contain very few with animals, forests, or anything comparable in complexity. Many planets could remain microbial for their entire histories, not because they failed, but because simple life is robust and sufficient. This thought changes the emotional shape of the search. Finding microbes elsewhere may be relatively plausible. Finding elaborate ecosystems with large organisms may be much harder. The universe might not be empty, but it may reserve complexity for only a minority of its living worlds. Intelligence may be one branch, not the inevitable direction of life. Humans often speak as though evolution has a destination, and that destination somehow points toward minds like ours. But evolution has no obligation to produce intelligence, let alone technological intelligence. It responds to circumstance, opportunity, and survival in local environments. On Earth, life spent immense stretches of time thriving without anything close to human thought. Countless successful organisms solved their worlds through speed, camouflage, cooperation, or sheer endurance, rather than abstract reasoning. Intelligence may therefore be a branch, one peculiar adaptation among many rather than the natural summit of biology. If that is true, then even worlds rich with life may never produce civilizations. They may remain full of beautifully adapted organisms that have no need to build tools, send signals, or contemplate the stars. This is one of the most important correctives in astrobiology. We are not necessarily the template. We may simply be one outcome in a vast evolutionary landscape that usually heads elsewhere. Civilizations might flicker briefly against cosmic time and vanish unseen. The age of the galaxy is immense, and that scale creates a sobering problem. A technological civilization may last for only a tiny fraction of cosmic history. Even if intelligent societies arise many times, they may not overlap in time often enough to notice one another. One species may build radio telescopes millions of years before another even evolves, or long after another has disappeared. In that case, the galaxy could host many civilizations across its history, while still feeling empty at any given moment. This is a haunting possibility, because it means absence of contact may say little about how often intelligence appears. It may simply reflect timing. Civilizations could be like brief sparks in a dark field, each burning brightly for a while, then going out before the next one ignites nearby. Cosmic silence would then be less about isolation and more about misalignment. The universe may have hosted countless minds, yet arranged them so they almost never meet. A galaxy full of life could still feel eerily silent. Silence does not automatically mean emptiness. A forest can feel silent from far away while teeming with hidden organisms. The same may be true on a galactic scale. Worlds may host microbes beneath ice seas, beneath clouds, or surface ecosystems that never produce technology. Even intelligent civilizations might avoid broadcasting exist too briefly or communicate in ways we do not recognize. If so, the Milky Way could hold abundant life and still offer us no obvious greeting. That possibility gives the silence a different emotional quality. It becomes less like abandonment and more like concealment. The galaxy may be biologically busy in ways that rarely translate into detectable signals. We are used to equating communication with presence because humans are. Noisy and technologically expressive nature may not work that way. Elsewhere, life can thrive without ever speaking to the stars. So the eerie silence around us may not be a negation of life. It may simply be the sound of forms of life not built to announce themselves. The famous silence of space may be a timing problem. If intelligent civilizations rise and fall across millions or billions of years, then overlap becomes the crucial issue. Two civilizations may each last 10,000 years, which sounds enormous on a human scale, yet still miss each other easily in a galaxy more than 10 billion years old. One may transmit before the other evolves. Another may begin listening after the earlier one has vanished. That means the silence we experience now may reflect chromology rather than rarity. The Milky Way could have hosted many intelligences spread across time, and yet our present moment may still be lonely. This possibility is both sad and strangely beautiful. It suggests a galaxy with a history of thought, curiosity, and perhaps wonder, but one in which those moments rarely line up. We may be listening in an empty interval between other eras of intelligence. The silence would then be real, but temporary in a larger sense. Not cosmic loneliness forever, only a missed appointment across deep time. Or it may mean intelligence chooses not to broadcast. Not every civilization would necessarily want to shout into the dark. Humans often assume that advanced beings would naturally transmit, explore, and announce themselves. But that may be a projection of our own restless habits. Another intelligence might decide that broadcasting is risky, wasteful, pointless, or simply uninteresting. It may turn inward, communicate through means we cannot detect or preserve. Strict radio silence as a cultural norm. Even on Earth, our own technological behavior has changed rapidly. We do not radiate in the same way we once did, and future societies may become even quieter. So the absence of obvious signals may not mean absence of minds. It may mean discretion. A galaxy of cautious civilizations could remain remarkably hard to detect. This possibility adds psychology and culture to the equation, which makes the puzzle even richer. Silence would not only be a technical condition, it could be a choice made repeatedly by minds that never felt any urge to call out, or we may be listening in the wrong language entirely. This may be one of the most unsettling possibilities of all. The search often assumes that intelligence will produce signals or artifacts we can recognize as artificial, but another civilization may encode information in ways far outside our expectations. Its communication may use unfamiliar frequencies, strange timescales, or physical principles we barely exploit ourselves. It may not resemble language in the human sense at all. We could be surrounded by signs and still fail to interpret them because we are listening with the wrong assumptions. This has happened many times in science. Data that later proved meaningful once looked like noise because nobody yet knew the pattern to search for. The same may apply to technosignatures. Our models are shaped by human engineering, human needs, and human imagination that makes them useful but limited. Another intelligence may not think, build, or transmit in anything like our style. The conversation may already be happening somewhere, and we may not yet understand the grammar. Even silence can be a clue if we read it well. A null result is not the same thing as no information. Every time surveys search a region of the sky and find nothing convincing, they still teach us something about the universe. They narrow possibilities. They tell us that certain kinds of loud, persistent, or easily detectable signals are not common in the places we have examined. Over time, that shapes our understanding of how rare broadcasting civilizations may be, how long they might remain visible, and what forms of technosignature are less likely. Silence can even push science in new directions by showing which assumptions are failing. If radio searches stay quiet, perhaps optical methods matter more. If obvious technosignatures do not appear, perhaps biology is common but technology is not. In this way, even the absence of a signal becomes part of the evidence. A dark does not only withhold answers, it also constrains them. A careful reading of silence can still move us closer to the truth. Some exoplanets are so extreme, they redefine what a planet can be. The first exoplanets shocked astronomers, not only because they existed, but because many of them seemed almost absurd. Some are giant worlds packed impossibly close to their stars, racing through full years in a matter of days. Some are bloated like heated balloons with atmospheres so puffed up that they barely resemble the compact planets of our own system. Others are scorched lava worlds, iron-rich bodies, or objects balanced on the blurry line between planet and failed star. Before these discoveries, the solar system shaped our expectations. We assumed planets should follow familiar categories with neat divisions between rocky worlds, gas giants, and icy outer bodies. The galaxy immediately broke those assumptions apart. It revealed that planets can be hotter, stranger, denser, lighter, and more dynamically arranged than the local examples around our sun prepared us for. That is why exoplanets feel so thrilling. They do not simply add to the catalog, they stretch the very meaning of the word planet. There are worlds hotter than some stars and stranger than fiction. That sounds like exaggeration until you look at certain ultra-hot giant planets hugging their stars at terrifying distances. On some of these worlds, the dayside is heated so intensely the temperatures climb beyond those of some cool stars. Molecules are torn apart, metals can vaporize, winds may race fast enough to move clouds of rock and metal around the globe. These planets are not just warm, they are chemical battlegrounds where ordinary ideas of weather begin to break down. One hemisphere may glow under relentless radiation, while the atmosphere itself streams away into space. Their skies may contain iron vapor silicate clouds or structures no one expected when planet hunting first began. What makes them so captivating is not only their violence, but their existence at all. Nature found a way to build and sustain worlds in conditions that sound less like planetary environments and more like furnaces. Fiction imagined strange planets, the universe made them real. Some planets may be made largely of carbon-rich crystal. Among the most alluring ideas in exoplanet science is the possibility of carbon-rich worlds, whose interiors contain vast amounts of crystalline material. If a planet forms in a system where carbon is especially abundant relative to oxygen, its geology may diverge sharply from anything familiar on Earth. Under enormous pressure, carbon can be transformed into diamond-like structures. On a planetary scale, it does not mean a sparkling jewel hanging beautifully in space. It would be a brutal world of immense pressure, heat, and darkness, with crystal-rich layers buried far below the surface. Still, the idea is irresistible, because it reminds us that planetary composition is not fixed by human expectation. A rocky planet does not have to be Earth like in chemistry. It can be built from very different raw materials and emerge into a completely different class of world. A planet made partly of crystal sounds like fantasy in planetary science. It may simply be one of nature's many ways of assembling matter. Other worlds may drown under oceans thousands of miles deep. An ocean on Earth feels immense, yet our seas are only a thin skin compared with what some distant planets may hold. Certain worlds may carry water layers so vast that they extend for hundreds or even thousands of miles downward. On such planets, the familiar relationship between sea floor and sky could vanish completely. There may be no continents, and perhaps no rocky bottom in direct contact with the liquid ocean. Instead, crushing pressure deep below may create exotic forms of high-pressure ice forming, a strange boundary between the upper ocean and the deeper interior. That means these worlds may be watery beyond imagination, while still being unlike Earth in crucial ways. Their surfaces might appear calm blue and inviting from afar, yet their deep structure could make nutrient cycling and life's chemistry very different. These are not simply bigger versions of our oceans. They are planetary water realms where depth itself becomes one of the defining forces of existence. The galaxy contains more possibilities than any single theory of life. That may be one of the wisest lessons modern astronomy has taught us. Every time we imagine we understand the likely settings for life, the universe widens the stage. It offers buried oceans on icy moons, warm candidates around dim red stars, thick atmosphere worlds unlike Earth, and planets whose chemistry may run on rules we are only beginning to grasp. Any single meat theory of life's preferred habitat risks being too narrow. Earth is our example, but not necessarily the template nature uses. Most often the galaxy may host environments where biology emerges through pathways very different from those that shaped our planet. Some settings may support slow, sparse ecosystems. Others may produce chemistry that mimics life so convincingly that we struggle to tell the difference. The bigger our catalog of worlds becomes, the less likely it seems that one elegant formula will capture them all. Life, if it is out there widely, may be a master of variation. Our first alien ecosystem may look more like a chemistry set. This is a helpful way to reset the imagination. The first extraterrestrial biosphere we detect may not resemble a landscape full of obvious organisms. It may instead appear as a network of reactions, gradients, dissolved compounds, and tiny cells interacting so subtly that the whole thing feels closer to chemistry than to the living scenes people usually picture. That would not make it disappointing. It would make it profound. Life begins by taking chemistry and pushing it into patterns of persistence, metabolism, and self-maintenance. In a hidden ocean, a porous rock system, or a plume from an icy moon, what we may first encounter is not a creature, but a biochemical process that refuses to behave like simple geology. The distinction could be delicate, yet that delicacy is part of the wonder. We may recognize an alien ecosystem first through transformed molecules, shifted ratios, or repeating metabolic signatures. Before life looks like a living world, it may look like chemistry that has crossed a threshold, or it may resemble Earth's strangest microbes in the darkest places. If life exists elsewhere, one of the best guides may be the organisms on Earth that already thrive where life once seemed impossible. Deep below the ocean, inside rocks and acidic springs, under Antarctic ice, and around hydrothermal vents, microbes survive under precious temperatures and chemical conditions that would have stunned earlier generations of scientists. These organisms show that life is not easily boxed in by human comfort. It can feed on chemicals, endure darkness, and persist in places with no sunlight at all. That makes them powerful analogs for alien habitats. A subsurface ocean beneath ice, a buried aquifer on Mars, or a chemically active rocky environment on some distant moon may host life more like Earth's extremophiles than anything visible on the surface world we know best. In other words, the galaxy's first familiar aliens may not be majestic beasts or forests. They may be humble, resilient microbes, thriving where almost nobody once thought biology belonged. Life could begin many times, and intelligence almost never. That possibility gives the universe a haunting shape. The transition from chemistry to simple life may happen whenever conditions are favorable. Enough perhaps on many worlds scattered through the galaxy. But the jump from simple life to intelligence capable of technology may be far rarer on Earth. Life arrived early, while intelligence like ours appeared astonishingly late. Billions of years passed in between, filled with survival, adaptation, extinction, and contingency. Nothing in that long history guaranteed minds that would build radio telescopes and ask questions about the stars. So the universe may generate biology readily. It almost always stops short of technology. If that is true, then worlds full of microbes may be common, while civilizations are rare beyond measure. This does not make life less impressive. It makes intelligence less inevitable. We often compress evolution into a story that seems to lead toward us. The cosmos may tell a different story, one where life begins often and reflective minds remain exceptional. The universe may be biologically busy, but technologically quiet. This idea helps reconcile two powerful intuitions. On the one hand, the galaxy contains so many worlds, but it feels difficult to believe life appears only once. On the other hand, the sky has not obviously filled with broadcasts, beacons, or unmistakable engineering. Perhaps both impressions are true. Biology may be widespread while technology remains scarce or short-lived. Many planets could host microbial oceans, subterranean ecosystems, or simple surface biospheres without ever producing anything like radio industry or planetary engineering. In that case, the universe would be busy in the deepest biological sense, while remaining quiet in the technological one. We would be surrounded not by communicative civilizations, but by hidden metabolisms, slow evolutionary experiments, and living systems that never announce themselves. That possibility is both comforting and eerie. It suggests we may not be alone in life, yet still be unusually alone. In a more specific sense, the galaxy could be full of living worlds and still sound almost empty. We are finally reaching the point where guessing becomes measuring. For centuries, the question of life beyond Earth belonged mostly to philosophy and imagination. People could speculate beautifully, but they had very little data. That is what is changing now. Modern astronomy is moving the subject out of pure wondering and into a new era of measurement. Telescopes can identify real planets, characterize some of their atmospheres, and begin testing which worlds are chemically promising. Spacecraft can sample plumes from icy moons, read the mineral history of Mars, and prepare the way for future missions aim directly at habitable environments. None of this has solved the mystery yet, but the style of the mystery has changed. We are no longer asking the question from complete ignorance. We are gathering evidence, narrowing targets, and learning how to read distant worlds in ways that would have sounded miraculous not long ago. This is a historic threshold. Humanity still wonders. But now the wondering comes with instruments sharp enough to answer back. A single confirmed biosignature would transform every field of science. Imagine the moment when a signal survives every challenge. The atmosphere is measured again and again. Alternative explanations fail, the data deepen rather than collapse. At that point, the discovery would no longer belong only to astronomy. Biology would have to rethink life as a universal phenomenon rather than an earthbound one. Chemistry would gain a second example of matter organizing itself into metabolism. Geology would be forced to consider planets shaped by living processes beyond our own philosophy, history, and even theology would feel the shock. A confirmed biosignature would be more than a scientific result. It would redraw the intellectual map of humanity for the first time. Life would no longer be a single instance mystery. It would become a category the universe produces. Even if the detected life were microbial and distant, the meaning would be immense. It would prove that biology is not a miracle confined to one planet, but part of the wider story written across the cosmos. A single confirmed technosignature would transform every human story. This would be an even sharper rupture because it would not only tell us life exists elsewhere, it would tell us that somewhere matter became conscious enough to build signal or alter its environment on purpose. That changes more than science. It touches identity, culture, politics, religion, and the deepest human narratives about uniqueness. A technosignature would imply not just biology, but minds. It would suggest that somewhere in the universe, another line of thought emerged from alien history and learned to manipulate energy in detectable ways. Even if contact never followed, the discovery alone would be overwhelming. Every human story about intelligence, destiny, and civilization would be forced to widen. Instantly, we would no longer be the only known example of a species that looked at the stars and became detectable because of it. That realization would ripple through everything. The first real technosignature would not simply be news, it would be one of the defining moments in the history of consciousness. A first proof of life may arrive as a statistical whisper that is one of the strangest and most likely possibilities. People often imagine discovery as dramatic and unmistakable, but the first convincing evidence may instead emerge from probability. Several observations may point in the same direction. A planet atmosphere may show a combination of gases that becomes harder and harder to explain without biology. Follow-up studies may reduce the plausible non-living alternatives until the remaining case becomes strong, not by spectacle, but by accumulation. In that sense, the universe may not shout. It may whisper through confidence levels, repeated detections, and patterns that gradually stop looking accidental. This would feel unsatisfying to some people at first, because it lacks the cinematic force of seeing an organism directly. But science often works this way. The deepest truths can arrive quietly building until doubt has nowhere reasonable left to stand. The first proof of alien life may not be a photograph. It may be a statistical argument so persuasive that the world slowly realizes it has crossed a threshold. It may also arrive from our own solar system first. For all the excitement around distant exoplanets, the nearest places may still win the race. That is because the solar system offers something no remote world can yet provide access. We can send probes to Mars, Europa, Enceladus, Titan, and other intriguing destinations. We can analyze rocks, directly taste clues, drill into samples, and eventually bring material back. These are huge advantages. A distant exoplanet may offer tantalizing atmospheric clues, but a nearby world can be tested with instruments on site. The irony is delicious. Humanity may spend years dreaming of life among the stars, only to discover that the first confirmed extraterrestrial biology was hiding on a moon or planet in our own celestial backyard all along. If that happens, it will still revolutionize everything. A second Genesis anywhere is enough. The solar system is not the grandest stage in the galaxy, but it is the one we can touch first. Sometimes the nearest mystery proves to be the deepest. We could discover alien life without ever seeing an alien body. This is worth sitting with, because it changes what counts as discovery. Many people instinctively imagine proof as something visible, a creature, a fossil, a microscopic cell under a lens. But science does not always require direct visual form. The world may reveal life through atmospheric chemistry, isotopic patterns, organized molecular structures, or environmental changes that strongly point toward biological activity. We might know something lives there without knowing what it looks like. In fact, that may be the most realistic path for a long time, especially for exoplanets. We may infer life from the way it transforms a planet rather than from any image of an organism itself. That kind of discovery would still be profound. It would tell us that living processes are at work elsewhere, even if the body behind them remains hidden. The first alien life may therefore enter human knowledge as evidence before appearance as process, before portrait, and as certainty without a face attached to it. The hardest part may be proving a miracle to cautious scientists. That phrase sounds dramatic, but it captures a real challenge. A detection of life beyond Earth would be so important that no serious scientist would want to accept it lightly. Every instrument would be questioned, every contaminant would be considered, every non-living explanation would be tested as hard as possible. This caution is not cynicism, it is respect for the magnitude of the claim. Extraordinary discoveries require extraordinary resilience under scrutiny, because history is full of exciting false alarms that dissolve when examined more carefully. If a real signal finally appears, it may spend years moving through argument, challenge, reanalysis, and independent confirmation before consensus settles. That means the first true discovery may feel frustratingly slow to the public. People may sense the miracle before science is ready to name it. Yet that slowness is what makes the final conclusion durable. When cautious scientists finally agree that life has been detected, the result will have earned its place beyond reasonable doubt. Every better telescope brings the question of life closer to Earth. That may sound backward because telescopes look outward, yet each improvement makes the ancient question less distant from human reach. Bigger mirrors, sharper instruments, better detectors, and more patient observing strategies allow us to examine worlds that were once entirely beyond meaningful study. A planet that used to be a faint dip in starlight becomes a body with measurable chemistry. A candidate atmosphere becomes a target for repeated scrutiny. A hidden ocean moon becomes a mission destination rather than a speculative dream. In that sense, technology keeps hauling the mystery inward. It takes a question once reserved for myth and philosophy and places it progressively closer to experiment. The answer may still be far away in space, but it no longer feels unreachable in principle that psychological change matters. With every generation of better telescopes, life beyond Earth becomes less like a poetic idea and more like a testable proposition moving steadily within range of human inquiry. We are living in the first era that can truly test this. That realization is easy to miss because we live inside it. For most of human history, even the boldest thinkers had no real way to investigate life beyond Earth. They had philosophy stories and nakedy skies. We have orbiting observatories, robotic explorers, precision spectroscopy, planetary missions, and a catalog of thousands of confirmed exoplanets. That does not mean we are guaranteed an answer soon, but it does mean something historic. We are the first generation with tools capable of moving the question from wonder alone into disciplined testing. Humans before us could ask whether life exists elsewhere. We can begin to check. That is an extraordinary privilege. The stars have always inspired the question, but only recently have they begun yielding enough data for serious pursuit. We happen to be alive at the moment, when speculation is turning into investigation. Whatever the answer proves to be, this era will be remembered as the one that first went looking properly. Somewhere, a living world may already be shining into our instruments. That is one of the most thrilling possibilities of all right now. Among the thousands of planetary systems already known, there may be a world where biology has taken hold and altered the air, the surface, or the chemistry in ways our instruments are beginning to detect. The signal may already exist in archived data, too faint or too ambiguous for us to interpret with confidence. Yet, or it may be crossing space at this very moment, entering telescopes as a subtle shift in starlight that will only later reveal its importance. This is what makes the search feel so immediate. The living world we seek may not be hypothetical in a distant future sense. It may be present in our observations, already waiting for better models, better measurements, or better luck. We are not only preparing for discovery, we may be standing near it with the evidence already brushing against our detectors while we work out how to read what it says. The search for life in space may change us first. Even before discovery arrives, the search is already reshaping human perspective. It has made us think more carefully about what life is, how fragile habitable worlds can be, and how unusual or ordinary Earth might prove to be. It has forced science to become more humble and more imaginative at once. We now look at microbes differently, at oceans differently, at atmospheres differently. Worlds once dismissed as barren are reconsidered. Planets once assumed to be unique are now seen as part of a vast population insurging outward. Humanity has also begun to understand itself in a new way as one biological. Experiment on one small world, asking whether others exist. That shift matters whether we find life soon or not. The search changes values, priorities, and self-understanding. It teaches patience, scale, and wonder. The first great transformation may therefore happen before any confirmed signal arrives. By asking the question seriously, we are already becoming different from who we were. As our journey through life in space begins to drift to a close, just take a moment to notice how fast it all feels now. We wandered past distant planets circling faint red stars. We passed hidden oceans sealed beneath ice, where dark waters may be moving in silence, far below frozen crusts. We traced the restless history of Mars, listened for strange signals crossing the sky, and followed the possibility that life may first reach us not as a face or a form, but as a whisper in chemistry, light, radio waves. We looked outward to worlds with no continents, to moons that cast plumes into space, and to planets so strange they seemed to belong to imagination more than astronomy. We followed the search from buried seas to alien atmospheres, from microbial possibilities to the distant chance of minds looking back across the dark. And through it all, one feeling remains. The universe is not smaller now that we know more. It is larger, richer, more mysterious, more alive with possibility. So now let all of that widen gently in your mind. Let the stars grow softer. Let the planets drift farther apart. Let the questions keep floating without needing answers tonight. There is nothing to solve, now nothing to hold. Onto just the sense of a great dark sky filled with unseen worlds moving slowly in their endless paths. If you enjoyed this journey, I hope you'll subscribe, leave a thought below, or return for another exploration soon. And if you happen to still be awake, there will be another video waiting for you on screen, ready to carry you onward through one more world of wonder. But for now, let your breathing slow, let your body grow heavy, and let the universe fade into stillness around you. Sleep well and good night.